Hello everyone, and thank you for attending today's webinar, Expanding Service Provider Applications for Pluggable Coherent Optics, sponsored by Acacia. Before we begin, I wanted to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your questions to our speakers. All questions will be captured, so if you don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget. Towards the end of today's presentation, we'll ask you for your feedback. A survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. An on-demand version of the webcast will be available approximately 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Heavy Reading's Principal Analyst, Sterling Perrin.
Hi, thank you, Becky, and hello and welcome everybody to Expanding Service Provider Applications for Pluggable Coherent Optics. And I am here today with Tom Williams. He's the Senior Director of Marketing with Acacia Communications, and along with me, he will be presenting and walking us through the next hour. So hi, Tom, and welcome to today's webinar.
Thank you, Sterling.
I believe for Acacia, this is maybe your first light reading webinar, so really happy to have Acacia on board and looking forward to it. For everyone,
yeah, we're excited to be here.
Yeah, no, it should be good. So everyone, you should be able to see the agenda. So if you look at the bullet points, I'll walk through the first one there, some optical networking trends and drivers, and then hand things over to Tom through the other bullets, coherent applications, network trends and challenges, and then he'll dive into the CFP2 DCO pluggable coherent form factor and product type, and then move into Q&A at the end. We should have about 10 to 15 minutes for questions. And also, we do have 2 poll questions today, so also looking forward to see what comes through those. In terms of introduction, I want to start with the main driver of optical networks in general, and that definitely is IP traffic growth, as we've, I think, talked through in many different forums. And the good news is there's a whole new set of different applications propelling IP traffic growth out into the future, the next 5 years and beyond. Probably largely lumped around migration to different mobile devices, not just handsets, but all kinds of connected things, IoT, cloud applications, the migration to the cloud, and then all things video. So that's the good part. But for optics, the point I'd like to make here is that it's not just about the growth in traffic. We have to understand that the optical industry is tasked with meeting those capacity demands while in an environment where the overall systems spend, optical systems spend, is essentially a stagnant situation, which is not always welcome news to the systems vendors, but it's a reality. The orange line there, so this is a normalized view of IP traffic volume as well as global optical transport system spend historically, so 2010 out through 2020 projected, so a combination of historic and projected. The orange is IP traffic growth. That's the great thing we see there, hockey stick. The blue line is the optical heavy readings forecast and historical data on global optical transport spend through 2020. And you can see at the systems level, the overall spend is actually very, very flat. There's ups and downs in optics, but if you take a view over the long term, it doesn't increase. And so that results in this gray line, descending gray line on the bottom, which is mapping your optical transport spend to IP bits for each year. And it's a continued sharp decline, dropping about 90% over the 10-year period. This is the reality of what optics needs to operate within, and obviously has done for decades. And the way it meets those demands is through really a series of transitions. Optical networks is always in a state of change and transition. And one of the biggest transitions we've seen over the past several decades is this migration to coherent technology, which I'll walk through here a little bit on this slide. So SONET was introduced, and this is going back to the 80s. SONET was introduced as part of the TDM era, and this was characterized by optical networks as a single channel, single laser, and your capacity increased by moving up the SONET hierarchy with different levels of TDM multiplexing. That was successful up until the Internet took off, and then what we needed then was a migration to WDM, wave division multiplexing. Here, capacity was increased by increasing the number of wavelengths on a single fiber, so starting with 4, 8, 16, and just kept scaling up. We had one move in channel rate increase from 2.5 to 10G, but then it really rode out the next decade or more at 10G, just increasing channels. The next transition, which is getting us up into the current situation of optics, was driven by the fact that we essentially exhausted the capacity of the C-band. You couldn't increase capacity simply by adding more channels. So then we moved back to increasing capacity per channel, but with some very big changes in order to do that. We needed, as an industry, more new multiplexing techniques, polarization multiplexing, orthogonal frequency division multiplexing, new modulation formats, phase shift keying, and amplitude modulation. And the common denominator for all of that innovation was coherent technology, the move from on-off keying to the sophisticated receivers characterized by DSPs, digital signal processors that could read phase, amplitude, polarization. And that really started with 100G, and that takes us through to where we are today. We're very much in the midst of the coherent era, but change within that as well, as Tom will talk through in his portion. The next 3 slides I'll go through, I want to highlight the major macro trends within optics. And then what we'll do is talk through the trends, and then Tom will map those to coherent and where coherent fits in, because coherent has a role in all of these. The first one is probably the most mature at this point, which is the migration to cloud and data center interconnect. And that was all driven by increased capacity. The starting point there is, if you look on the left, growth in server and rack input-output bandwidth, capacities per servers and racks continuing to scale up to a point in 2020. What Heavy Reading is forecasting at this point is you can get to 100 gigabit input-output per server, and with more servers per rack, you can get to 10 terabits per rack. And what happens is that increase really blasts right throughout the entire data center. If you look in the middle, affecting your connections for top of rack, your connections for leaf and spine, all scaling to higher and higher capacities. And then scaling out from there, those data centers need to connect with one another. And this is really where the coherent technology has come into play today and over the next couple of years. The interconnection between the data centers, moving first to 100 gig, and really that's what spurred a lot of the 100 gig growth, particularly in the metro, to 200 gig as well, and then scaling up to 400 gig and higher rates as we move forward. The next macro trend in optics is one that's definitely new compared to the DCI, and this is 5G and the impact on the network, on the optical network. Clearly, this coming 5G era is not just about the handsets and the sensors and other devices, but the wireline network has a critical role in access, in metro, and the backbone. If you look at the chart on the right, which was supplied to us by Ericsson, every bit of that has an optical implication as we move to 5G, right up to the cell tower. But for Coherent's probably not going to play in all of those. But if you look at that dashed box there, and if you look moving into metro, regional, and aggregation networks, as well as the backbone networks, as the front haul, mid haul, backhaul network scale, all of that, you need to have increases throughout your metros and backbones as well. This is where Coherent plays in. This is where 100, 200 gig, and I guess potentially beyond types of data rates would come into play. So 5G, preparing the wireline network for 5G applications on a wide scale, this needs to be done. This is a very critical trend over the next couple of years in advance of really wide-scale rollout of 5G. final trend I'll hit on before I hand things over to Tom is on software-driven automation, or kind of under the umbrella term of SDN. And this probably started about 5 years ago as a macro trend, but is still fairly early stage in reality, at least at the packet optical networks that we look at. Operators realized several years ago that hardware-based innovation alone is not going to scale to meet. You think back to that first chart I showed with the scaling capacity, but that real constraints on spend at the optics level cannot be done by hardware innovation alone. So really looking forward, it's a combination of software-centric innovation, SDN, as well as continued innovation in the hardware. Originally, SDN centered around the packet layers, primarily around layer 3 IP, but what we've seen over the past couple of years is a really big move of SDN into the optical layers as well. And I've highlighted just a couple high-profile projects that are either 100% focused on optics or have optics components to them, just to make this point. The TIP Voyager, which is part of the Facebook started but now very broad initiative, the Telecom Infra project. This is a disaggregated packet optical transport box, merchant components, as well as SDN control. We also have the AT&T's, at least AT&T started Open ROADM MSA, which is also starting to get broader draw of network operators, a disaggregated ROADM architecture. Here we're looking at multi-vendor commodity hardware and open APIs, and again, SDN control for that. And then finally, Cord, which is now part of the Linux Foundation called Open Cord, and has many different components to it, but optics has a fairly big role to play here as well, particularly on the access side. So I make these points because these are really the three major macro trends that we're following for optics. I think will drive us over the next couple of years, but also because the Coherent technology, which I talked about in the very beginning, that has a role to play in each one of these as an enabler and as a way to move these forward. So they are very tightly interlinked. And as I said, we are very much in the midst of this Coherent era right now. Probably maybe no better company to talk about this. Certainly one of the major innovators in driving Coherent innovation over the past couple of years is Acacia. So that's one of the reasons why I'm very happy to have them on today. And with that, let me move things over to Tom to take us through a look at Coherent applications and start tying those to some of what I've talked about. Tom, I'll let you take it from here.
Thanks, Sterling. I'd like to follow up on some of the broad market trends that Sterling discussed and delve more deeply into some specific applications and architecture trends in the optical interconnect market. In particular, I'll focus on coherent optical interfaces in a pluggable form factor. Coherent technology was first introduced in long-haul applications to overcome impairments that required complex module compensation techniques when using direct detection. Leveraging advanced CMOS processing nodes and reduction in design complexity, coherent solutions have moved from long-haul to metro and even shorter-reach optical interfaces. When Acacia introduced a CFP DCO module in 2014, Coherent became an even more compelling solution for metro and DCI applications. Today, Coherent is moving from metro core to access aggregation networks. And looking forward, the industry is working to standardize coherent solutions for even shorter reach interfaces. This model of new technology adoption in long-haul interfaces, followed by a migration to shorter reach applications, has been demonstrated in the industry before. The transition from copper to fiber optics followed a very similar path starting in the 1980s. Technologies such as wavelength division multiplexing and forward error correction also followed the same pattern. It's anticipated that Coherent will be no different. Recognizing this trend, coherent standardization activity is currently taking place in several organizations. The Optical Internetworking Forum, or OIF, has an ongoing project to define a coherent standard for DWDM interfaces in data center applications with reaches up to 120 kilometers. Cable Labs has announced a project to define coherent standards for cable access networks, and IEEE is considering coherent for unamplified applications beyond 10 kilometers. All of this standardization activity reinforces the view of coherent moving to shorter reach, high volume applications. Beyond 400 gig, it is likely that Coherent will be used in even shorter reach interfaces. Today, Coherent technology is being deployed in a wide range of applications, ranging from tens to thousands of kilometers. While network operators in each of these markets need to manage capacity expansion at the lowest cost, differences in architectures and demands drive a unique set of priorities for each application. I'll explore some of these applications and the factors that drive solutions for their optical interconnect requirements. The long-haul market, where Coherent was first adopted, is still a large segment of the Coherent ports shipped each year. This market is highly sensitive to performance because longer reach interfaces eliminate the need for additional costly regeneration. The parameter most commonly used to evaluate the performance of optical interconnections in DWDM networks is optical signal-to-noise ratio, or OSNR. OSNR describes the relative energy of the signal carrying the information to the energy of the noise from other sources. Optical receivers are specified based on their ability to detect the desired signal in the presence of noise. Why is OSNR so critical to long-haul DWDM networks? Optical signals are amplified as they are transmitted across the network. At each amplifier, the signal is degraded slightly, meaning the level of the noise is amplified relative to the signal. When the signal level is so close to the noise that it is nearly undetectable, it needs to be regenerated. At a regenerator, the optical signal is converted to the electrical domain, where the data can be accurately decoded. The same data is then recoded, retimed, and converted back to the optical domain with a high signal-to-noise ratio, capable of passing through additional amplifiers. Higher performance optical interfaces allow longer reaches without needing regeneration, which ultimately lowers the cost of deploying and managing these networks. In today's optical networking market, 100 gig QPSK modulation is still widely used in long-haul networks because it offers exceptional performance. Using 100 gig QPSK, fiber capacity can be further enhanced by reducing channel spacing from traditional 50 gigahertz to 37.5 gigahertz. For some network operators, 200 gig transmission based on 8 QAM modulation can be a compelling alternative. Transmitting 200 gig per carrier can lower the cost of the optical interfaces by transmitting double the capacity over the same optics, but it does come with a penalty. The higher order modulation, typically utilized to achieve higher data rates, requires increased OSNR at the receiver for error-free detection. Initial 200 gig solutions in the industry were based on 16 QAM modulation using the same baud rate as 100 gig QPSK, which has the benefit of supporting the same 37.5 gigahertz channel spacing, but results in a significant OSNR penalty. Recently, solutions have become available using 8 QAM modulation at an increased baud rate. This approach can support 50 gigahertz channel spacing with OSNR performance that is better than 16 QAM. Coherent interconnections have also been widely adopted in metro core networks. The dynamics in these networks are somewhat different from long-haul. Metro core networks usually consist of many ROADM nodes where wavelengths are dropped, added, or routed to other destinations. This is done using wavelength selective switches, or WSSs. Each WSS is effectively an optical filter that can narrow the total bandwidth of the channel. Passing through multiple ROADM nodes can result in significant narrowing of the available spectrum of the complete optical path. In addition, these WSS can introduce additional impairments, such as polarization-dependent loss. Though the reaches in these applications are less than long-haul, they still require a high level of performance due to many link impairments. Metro networks are not entirely about optical performance, though. Central offices can often be crowded and power limited. High-density solutions that are power efficient can be particularly valuable in these applications. In addition, metro networks handle a wide range of traffic. These networks quickly become complex to manage, with different equipment required depending on the application. Common solutions can be leveraged across multiple platforms, support a wide variety of traffic types, and scale capacity in a cost-effective manner can allow network operators to manage their operational costs more effectively. In the last 10 years, the optical networking industry has been transformed by the requirements of large cloud network operators. High-capacity interconnections are necessary between these hyperscale data centers to enable cloud functionality. These connections between data centers differ from traditional carrier networks in that they're usually point-to-point with no ROADMs in between. These data center interconnections, or DCI, can be within the same city or across oceans. Cost and power are generally the most critical parameters for these applications. Some use cases can be fiber constrained, making spectral efficiency a higher priority, while other use cases have more fiber available. Customers in these markets tend to be early adopters of new technology, and they have shorter product life cycles. They're open to engaging in a variety of commercial modules, and some of these network operators have very advanced teams with extensive experience developing optical networking solutions. Large cloud network operators, along with some more traditional carriers, are driving changes in how network functions are partitioned between vendors, allowing them greater freedom to transition between vendors and product generations with minimal changes in the software used to control the network. Access networks are an emerging opportunity for coherent interconnections. The cable industry is taking the lead in this segment by driving standardization of coherent for access aggregation network requirements. As the hybrid fiber coax or HFC networks evolve toward fiber deep architectures, remote PHY implementations are gaining momentum with the MSO community. This transition drives 10G optical interfaces closer to end users, resulting in aggregation points in the network where 10 to 20 remote PHY devices based on 10 gig Ethernet come together. Coherent can be an effective way to transport these aggregated signals back to the hub. In some cases, it may be necessary to transport a single coherent wavelength back to the hub, but since coherent is inherently a DWDM technology, this approach provides the capability to expand capacity by up to 2 orders of magnitude in the future. Cable Labs is the standards organization of the cable industry and has recognized the need for this solution in the market. Earlier this year, they kicked off a project to define coherent standards for cable access aggregation applications. This project includes participation of many leading optical networking vendors, as well as several large MSOs. Another emerging access application is 5G backhaul, as Sterling mentioned. While there is still uncertainty in the exact timing and implementation details of 5G networks, it's clear that backhaul demands in wireless networks are going to need to increase significantly. As more capacity is delivered to end users, the connections back to the core network must scale as well. Coherent offers several benefits in these access aggregation applications compared to traditional direct-detect solutions. At higher data rates, it becomes very challenging to deploy direct-detect solutions over tens of kilometers without using dispersion compensation. Alternatively, solutions may consider many parallel optical interfaces, but that drives up the cost of the solution. Today's coherent implementations are generally based on tunable laser technology. While fixed laser implementations are a consideration in these applications, tunable solutions can offer operational benefits by significantly reducing the number of spares that need to be stocked. Tunable solutions also tend to support shorter lead times, accelerating the ability to turn up new services. Finally, coherent solutions are future-proof with the ability to scale capacity by increasing data rate or adding additional wavelengths. Adoption of coherent technology in access networks could offer an additional benefit that may not be obvious at first. Since the same solutions can address a wide range of network interfaces, it may be possible to collapse the supply chain for multiple applications into a single solution. For example, the same optical interconnect that is used for access aggregation may support metro and regional interfaces, potentially offering significant efficiencies for network operators. The last application that I'd like to discuss is an unamplified point-to-point interface. These are essentially client optical interfaces for connections between buildings. As data rates have increased, it has become more and more challenging for direct-detect solutions to address these kinds of applications. At 100G and 200G, proprietary coherent solutions are already used for links in the 40 to 80 kilometer range. Looking forward to 400 gig, this application is within the scope of the OIF ZR project, In addition, the IEEE study group that is considering solutions for 10 kilometer for data rates of 50 gig, 100 gig, 200 gig, and 400 gig is evaluating coherent alternatives for these applications. Since these interconnections are not amplified, they're not characterized by their tolerance to low OSNR. In these applications, transmitter power and receiver sensitivity are the parameters that define the usable link budget. Coherent detection offers the same increase in performance for power-limited sensitivity as it does for noise-limited applications. In addition, volumes in these applications can be very high, and coherent implementations will need to be cost-effective and extremely power-efficient. That brings us to our first survey question. Sterling?
All right, yeah, thank you, Tom. So let's take a break here and get some thoughts from you, the audience. Hopefully the poll question is up in front of you. Which application do you believe will be the most influential in driving the next phase of coherent growth? So basically, Tom has walked through each of these, and we just want to get a sense of what's resonating most with you. If you're a service provider, then answer on behalf of your own organization. If you're a supplier in to the service providers, then where your customers, what are they telling you? What are your thoughts from those? Long haul, metro, data center interconnect, cable access, as Tom has just walked through, wireless backhaul, getting ready for 5G, and then the last option is unamplified interfaces. And so let me just get a moment for this to reach a critical mass here, and when we get there, we'll preview the results before I push them out, just to make sure we have enough folks coming in before we get there. Yeah, no, just my own interesting to meet, Tom, the cable access, which you just mentioned, is something I've just kind of clued in on myself based on some interactions. We know the industry is going to be very much coax focused as the cable companies for that connection into the home itself, but I'm realizing how much that fiber is pushing more and more deeper into the closer to the home. So you're sort of like taking that coax and snipping it here at different points throughout the network. Obviously, the very last leg they would snip out would be the actual connection to the home for cost reasons, but there's still a lot for fiber to be done there, even while that end run is remains coax. Let me push these here, and let's see what we're getting. Tom, hopefully you can see the results. Let me just do a second push in case we got a late bloomer. All right, great. So it looks like metro about 37% on my read here, and then DCI 35%, and then kind of falls off from there. Wireless backhaul, very small, and actually long haul fairly low. Any thoughts on these? Any surprises? Kind of how you thought it would come in?
Yeah, I think it kind of speaks to the timing of those markets. I think long haul is probably small because it's already a large market, so not necessarily viewed as the growth driver. And I think some of the more emerging markets are maybe a timing question of when they happen, whereas metro and DCI are kind of in the sweet spot today.
Yeah, no, exactly. Like I just said, the cable access, I kind of got clued into that. Seems like some folks are already clued into there with the wireless backhaul. Probably some more work to be done and kind of making the case for that. Great. Let's keep going. I'll hand this back over to you to go through network trends and challenges.
Great, thanks. So yeah, next I'd like to review some trends and challenges faced by the optical networking industry, particularly as it pertains to coherent. So disaggregation, we've alluded to a bit earlier here, but it's a common topic at industry conferences and events today, and it describes the partitioning of network functions into individual elements so they can be sourced separately. For transport networks, that basically means three main functional elements of the transponders, the open line system, and the control plane. And there's a few reasons why the network operators want to disaggregate. Supply chain flexibility is one reason. And by partitioning the network elements, they're able to make separate purchasing decisions for each of the individual functions. They combine this with a multi-sourcing strategy. It provides a more competitive landscape for the network operators to make purchasing decisions. The second reason, though, is disaggregation gives them the ability to accelerate time to market by leveraging a common control plane across multiple product generations. So this can be done by defining a common API for the control functions that are generally used for transport networking operations. And if this common API can be defined in a way that it's no longer coupled to the hardware implementation, it allows the same control plane to be used across multiple vendors and multiple product generations. The disaggregation that we see taking place at the network level is in contrast to the integration that is taking place at the component level. In both silicon photonics and indium phosphide, integrated photonics are becoming a critical technology necessary to achieve the cost, size, and power reductions in order to keep pace with increasing bandwidth demands. So another trend in the industry is the integration of transport optics directly on the switch or router. This eliminates the need for external transport equipment and additional client optics necessary to connect to that transport equipment. In addition, it also reduces the need for a control plane to interface to an additional network element, resulting in a more seamless operation of the network. With coherent solutions, a wide range of network applications can be addressed using this architecture. The model has been used sparingly in the past because of the relative size of transport optics compared to the high-density client optics. As pluggable coherent module solutions are getting smaller and lower power, it's increasingly possible to leverage the benefits of this architecture with minimal, if any, loss in switch capacity. Another trend we're seeing in the coherent market is the evolution toward high-density pluggable form factors. Coherent solutions have evolved from large, discrete line cards to board-mounted modules, and then ultimately to pluggable module solutions. There's still a place in the industry for high-performance board-mounted modules, but pluggable coherent optics tend to be the space that brings coherent into new market applications as we discuss some of these emerging markets. Acacia's coherent CFP module was the first pluggable coherent module to be widely deployed, and the module was designed with power optimization in mind at a time when most coherent solutions were only focused on optimizing performance. Through extensive algorithm optimization, the power of the DSP was lowered to fit within the profile of the CFP form factor. This pluggable architecture with the DSP internal to the module is referred to as digital coherent optics, or DCO. The CFP DCO module opened up new metro and DCI markets to coherent that would not have adopted the more costly solutions based on discrete optics. The next pluggable solution to enter the market was based on a different architecture. Analog coherent optics, or ACO, contains the optical components necessary for coherent transmission. But the DSP is moved outside the module to the host board in the ACO architecture, and you have a high-speed analog signal that transmits across the module connector. This architecture was able to enable a CFP2 ACO solution that supported 100 gig and 200 gig transmission. Today, Acacia is delivering a CFP2 DCO module that supports 100 gig and 200 gig operation, which gives you the convenience of a DCO interface with full functionality and full data rates. By increasing the density and reducing cost per bit, this solution is well positioned to satisfy the requirements of emerging access networks, in addition to the more traditional carrier, metro, and long-haul markets, including DCI. Looking forward, as the industry moves to 400 gig, coherent solutions appear to be well positioned for adoption in even shorter reach applications. All of this is driven by integrated photonics and power-efficient DSP design. As pluggable coherent modules have transitioned to smaller form factors, their value to network operators increases. Regardless of what kind of system they are plugged into, these digital coherent modules offer the same electrical and management interface as widely used client optics. Smaller pluggable form factors allow more modules on a line card, further increasing the capacity CapEx savings that can be achieved with a pay-as-you-grow model. Pluggable modules also offer a high level of field serviceability when maintenance is required, which results in OpEx savings. These high-density pluggable solutions achieve real cost savings for network operators. We're going to move now to some industry challenges. Coherent interfaces have improved optical interconnect performance in many ways, but there's a few potential impairments that are unique to Coherent. Today's coherent systems are all based on transmission of data in two polarizations. This doubles the spectral efficiency of coherent transmission because the two polarizations share the same spectrum. The digital signal processor recovers the polarization alignment in the receiver. In general, this results in a very cost-effective means of increasing fiber capacity. In real-world deployments, network operators have observed scenarios that can cause the polarization of the light traveling down a fiber to rotate at speeds faster than the DSP can track. Events such as lightning strikes or acoustic vibrations caused by trains can cause polarization rotations at speeds an order of magnitude higher than typical. Aerial fibers can be particularly sensitive to these events due to their exposure. Since aerial fiber can be more prevalent in access networks, it's important to better understand the potential susceptibility in these emerging coherent applications. The industry is gathering data on the frequency and magnitude of these transient events, while DSP designers are working to improve the ability to track these fast rotations and ensure that they recover quickly when errors do occur. Acacia has been working closely with our partners on these issues for several years to make certain that our coherent solutions are robust in all types of environments. We'll put a few numbers behind this discussion. Under normal conditions, SOP rotation is generally way below 100 kiloradians per second. These rotation speeds are easily managed by existing DSP solutions. But when transient events can occur, the rotation can accelerate to more than 1 megaradian per second, which has caused some issues for some implementations. Our Maru DSP, which is used in our CFP2 DCO module, can track rotations at over 3 megaradians per second in 100 gig QPSK mode without passing any uncorrected errors. I'd like to close by discussing a specific pluggable coherent implementation, the CFP2 DCO. At Acacia, we believe the CFP2 DCO can be a form factor that can span across multiple product generations. Today's implementations are based on 100 gig and 200 gig transmission, but the form factors being standardized for applications up to 400 gig. New platforms supporting 400 gig could be developed and brought to market with existing 100 gig and 200 gig optics. When 400 gig module solutions are available in a CFP2 DCO form factor, system vendors would be able to quickly bring them to market. This backward compatible model is analogous to client optics, where the industry has used multiple generations of the SFP family of modules for client optic applications. It's a strategy that's been proven over and over again in the optical networking industry. As an example of the potential design efficiency of this model, the diagram on the bottom left of this slide shows a simple transponder daughter card. This card can be supported today using 100 gig QSFP28 client optics and Acacia's CFP2 DCO module. Without redesigning the card, it could then support 2 by 200 gig QSFP56 modules connected to a 400 gig CFP2 DCO. While next generation designs are targeting higher density 400 gig form factors such as OSFP and QSFP-DD, the larger CFP2 form factor offers the ability to integrate more functionality and can manage higher power dissipations. I'd like to discuss a couple of CFP2 DCO use cases that have been provided by our partners at ADVA. In this one, we're highlighting the metro network expansion driven by the growth of cloud services. While this capacity is often delivered by traditional carriers over their metro networks, the bandwidth growth is driven by cloud and over-the-top services. This is an example of how some of the applications we've discussed are often interrelated with one another. These networks are generally run in 10 gig wavelengths today and need a cost-effective and power-efficient upgrade path to 100 gig and 200 gig capacity per carrier. The second ADVA use case is the cable MSO application that we highlighted earlier in the presentation. ADVA's FSP 3000 Access Connect product offers a high-density solution to perform aggregation of 10 gig lanes and coherent transmission at 100 gig or 200 gig. Leveraging ADVA's micromux technology and Acacia's CFP2 DCO module, this solution is well suited to the requirements of this emerging coherent access market. In closing, we've discussed a range of applications, industry trends, network challenges, and architectures. We believe these industry forces are all favorable to compact pluggable solutions like our CFP2 DCO module. As we've discussed, the pay-as-you-grow model and field serviceability enables reduced CapEx and OpEx costs. In addition, OIF standardization and support for 100 gig, 200 gig, and 400 gig data rates makes it an investment in CFP2 DCO future-proof. The module is designed to offer a combination of power and performance that offer value to network operators in traditional as well as the emerging coherent applications. Acacia's CFP2 DCO module recently completed qualification and is generally available in production volumes. It has been well received by customers, end users, and analysts alike. Industry momentum is shifting toward DCO architectures, and CFP2 is well positioned as a multi-generation form factor. With that, I'd like to turn it over to Sterling for the second of our survey questions.
All right, thank you, Tom. Right, so that concludes the presenting portion. So let's move into a poll question here, and then we'll dig into the Q&A. We definitely got about 15 minutes for questions if you have them. So we have a few in, but please ask away now, and we'll get through as many as we can. In the meantime, let's put out the poll question. What feature of pluggable coherent optics offers the most value to end operators? Again, if you're an operator, network service provider, answer on behalf of your organization. If you supply into the operator service provider industry, answer on behalf of your customers. Pay as you grow is the first option. Field replacement, transport optics in client sockets, and the last option is leverage well-known form factors. With that, let me leave that up a bit, and let's see if we can take a poll, an audience question in the meantime. Let's see. So, Tom, the question is, can you explain the reasons why pluggable DCO can reduce CapEx and OpEx for network operators? So I had presented a slide in the beginning where you really need to be able to scale, but your cost environment is going to be very constrained. So maybe if you can connect the dots a little bit more directly about the role of pluggable DCO in helping reduce those costs.
Sure. I think there's a handful of different reasons why I can save on both CapEx and OpEx. We talked during the presentation about the pay-as-you-grow model that I think is pretty well understood in most of the industry, but basically you can your initial investment, you only buy the capacity that you need, but the card may be able to support additional ports that could be turned up at a later date. So you defer that cost until the time when you need to deploy instead of buying it all up front. A second reason, if we look at the comparison between DCO and ACO, there's efficiency in the manufacturing and test, because the DCO is integrated and tested one time as opposed to individually testing the DSP and then the optics and then doing an additional test once they're integrated together, whether that's in a manufacturing environment or actually in the field. In all of those cases, I think the integrated photonics are a driver in terms of savings in the CapEx and driving to lower cost. On the OpEx side, I would add, I think I mentioned a bit in the presentation, the field repairability. Again, you can do that on an individual unit instead of having to pull an entire line card if you had multiple ports on the line card. And then the final one that I would mention is we get feedback from carriers that one of the challenges they face is that all their the systems all have different maintenance and operations kind of guidelines and procedures. And so getting to a more common, interface that is supported by multiple different systems makes it easier to manage the network and get to some common operational procedures.
Okay, excellent. And I have just pushed the poll results. I think you touched on actually some of these points as you walked through some of those benefits. It looks like the pay-as-you-grow, 43%, that came in as the top. The second option coming in, transport optics in client sockets, 26%, pretty high number, and then field replacement, a third, although fairly distant at that point. Again, any thoughts, any surprises, or is that how you thought this would come through?
I wouldn't say any surprises. I think certainly pay-as-you-grow is the most obvious benefit that stands out. I think the transport optics, 25% there is kind of a confirmation that model is finding a home in some applications and is certainly pretty relevant today.
Mm-hmm. Yeah, no, I was very interested in that one. Let's go through some more. We have a lot of questions coming in, which is great. Kind of thought we would. Glad everybody's alert and engaged this close to the holiday season. Let's see. Question from a network operator. Do you expect that the OSNR, optical signal-to-noise ratio tolerance, as you described, do you expect that the OSNR tolerance for CFP2 DCOs will be better than the current 24 to 25 dB? That's the question, and then it looks like a comment. This is pretty limiting in terms of ROADM network hops. Can you take a shot at that one?
Yeah, I think certainly without getting into specific details on performance specifications, I think we view certainly the CFP2 DCO supporting long-haul applications and metro applications with multiple ROADM hops, and certainly quite a bit better than the 24, 25 dB reference there is achievable in the CFP2. Okay.
Good news then. This is an interesting question on standardization. Do you think standardization of coherent optics will result in increased competition is the question. I guess I would add a little addendum to that. Is that good? If so, is that good for you or a negative for Acacia?
Sure. Yeah, I think it's a great question. We're big supporters of the standardization activity that is going on because we think it's an important step for coherent to be adopted in certain types of applications. As we move toward some of these higher volume applications, those are going to need to be standardized. And as the overall, kind of going back to the slide you presented in the beginning, as you move toward different technology phases, we recognize that there's going to be investment in these coherent applications as that's where as the TAM moves toward. So I think we embrace the competition. At the end of the day, innovation is required, and we think of ourselves as innovators, and a competitive market sometimes reinforces the fact that you're in the right market.
True, but right, you have had a bit of as a merchant, or I guess a merchant supplier, you've had a pretty good, you had a good lead in some of the more advanced applications, and it looks like it probably is going to get more competitive. So we'll see where that goes, but interesting trend for us to watch as well. Let's see. Yeah, you had talked a little bit about dispersion compensation, and you'd referenced that in the 5G application. So the question is, with respect to 5G, can you explain what you mean by dispersion compensation and maybe just flesh out that issue a bit more and why it's relevant in this particular application?
Yeah, sure. So what I'm referring to here is dispersion compensation that is external to the module, kind of in the link. And what happens is direct detect technology. If you're a 10 gig transmission of tens of kilometers is pretty easily supported, and there's a lot of solutions that can do that. As the baud rate goes up, the reach, the dispersion limit is a squaring function with reach, and so your reach gets, when you double the baud rate, your reach gets cut by a factor of 4. And so it starts to become very difficult when you go to, say, 25 gigabaud, very difficult to achieve any kind of performance in the tens of kilometers range without having external dispersion compensation, which can be difficult to manage in these access networks where every link is probably a little bit different than another one. It's not like you're going to have a one-size-fits-all solution. So that becomes pretty challenging. Coherent inherently is able to handle the dispersion. There's no dispersion compensation in the long-haul interfaces. The dispersion compensation is done electrically in the DSP. And so these are actually a scale down to do tens of kilometers is a significant scale back of the dispersion compensation that is in today's Coherent products. But it makes managing the network much more straightforward. So I think it'll be, as you look at some of these benefits of Coherent, obviously some of the solutions that are available today are at cost-effective points, and we'll have to monitor when those crossover points happen, where the data rate gets to a point where it makes the performance advantage of Coherent worth the price delta, and obviously that price delta is shrinking over time as well.
Mm-hmm. Right, and I guess as we get more and more into the access area, you're really looking at things that used to be probably largely 10 gig networks moving up to 100 gig and beyond, which is where the Coherent really comes into play.
Right, and I think what you're forced to do is you look at multiple lanes of parallel 10 gig, and so if you're doing 10 by 10 versus 100 gig Coherent, what's the relative cost of those types of solutions and versus the crossover point where it makes sense? I
see. Right, good point. So question about actually there were a couple questions on this, which also showed through in the poll, the integration of those client type optics into the switch router. There's a couple questions that touch on that here. One, do we have Ethernet switches routers today already fully supporting CFP2, DCO, DW, DM uplinks? Or is that a future development, I guess, for the systems guys, the switches and routers?
So I guess it's not our place to make any product announcements for our customers, but I would say we anticipate that there will be solutions available.
Right. I know just from my set, as I said, there is a tremendous amount of interest in that. And I can't say for sure on the vendor side myself. I do know, like if you look at the Arista work, they're very interested in moving out of the data center into data center interconnect with populating their own switches with these longer reach optics. Basically anybody that's in the switch router business would see this as a big opportunity. I don't myself know personally if we've had any announcement the CFP DCO as you guys in it. That was just commercially available, I think. Was that announced this week? It's very new, correct?
Yeah. So we announced that. Yeah, we announced that the module is generally available. So we're in volume production at this point, and but we leave the system announcements to our partners.
Sure. Let's see. Interesting. Let's see. This one needs to be parsed through a bit. Again, on the idea of the client slot use of these types of optics for the longer reach data center interconnect. The term plugging transport module and client slot may not trigger the realization of two extremely significant advantages. I guess this is more of a comment, but you might comment on the comment. Two significant advantages: reducing number of points of failure and of network simplification, one less connection. I guess it's a point. It's a bit of a sub-point, I guess, to the original. Maybe you can talk about just let's kind of expand the issue a bit. The pluggable optics on the switches and routers for connecting data centers, you are reducing those DWDM systems in between in doing that. You're connecting the two switches and routers. Maybe you can address two issues and questions, Tom. One is, historically, there was that faceplate trade-off. It seems like you're suggesting here that at least when we get to 400 gig, the size of the Coherent versus the size of the client optics for 400 gig will be the same, so we may not be in a point of faceplate trade-off. Is that the expectation? And then two, if you can, beyond just the ability to get more capacity on the box, these other issues that have been brought up in the question, maybe address if there's other, if you're seeing these resonate as well. So kind of a two-part, but kind of holistically addressing this plug the optics into the router topic.
Sure. So, yeah, and I think you're right. I think if you look back at, generations of products, that gap has gotten smaller and smaller, and I think 400 gig is where we're targeting the trajectory to intersect. And I think at 100 gig, 200 gig, the gap is very, very close to CFP2 supporting 200 gig relative to a QSFP 28 supporting 100 gig. The 28 is probably a bit higher density, but it becomes a more manageable trade-off. I think actually some of the points that were made in the question are relevant and probably an extension of some of what I alluded to in the simplification of the network operations. I looked at it from the control plane perspective, that you eliminate one interface there, but you're also simplifying the turn up of equipment. You're eliminating a additional point of failure, whether that's because of connector issues or you have additional lasers and receivers and points of failure by adding additional optics. And, all of those things end up being a question of the trade-off, right? When is the density close enough? When is the relative price transitions and all of those things? So, and sometimes that is different end users weigh those trade-offs in different ways, right? So some end users look and put a high value on having one network element to control and see a big value in plugging the optics directly into the switch. Other end users look and say, nope, I'm not willing to make any trade-off of the capacity until they're in the exact same form factor. I'll have an external transport box. And so, these things don't tend to be, crossover points that are very fair. They tend to be a transition as solutions get more favorable and able to be closer and closer to ideal, then a higher percentage of the customer base swings over.
Right, and I guess you kind of alluded into my follow-up question on that, but let me just kind of put an end cap on this one. I think we can do one more question after this. So, if I'm reading you right, you're saying that even in the absence of that, of maybe density parity, so the simplification, so you do see some customers will go for the simplification argument. That is compelling enough for some set of the market, even in the absence of hitting the equal or greater density on the Coherent side?
Yeah, I think there's customers that exist today who already are willing to make that trade-off. I mean, there's customers who would make that trade-off even in earlier generations. But I think what is happening is as the gap gets smaller, you get more and more transition over toward that model.
I see. Right. Good point. We should have for everybody the survey. We have a brief survey, which we always do on our webinars. If you can take a moment to fill that out. And we are at the top of the hour. We have actually a ton of questions we didn't get to. Really, obviously, a very good topic, and a great job, Tom and Acacia, on this one. The last question I'll leave out, I'll leave you with is, do you think the coherent industry is moving towards more specialized DSP development? And rather than a simple yes, no, I think you're going to say yes. Maybe kind of describe what that looks like.
Yeah, I think that's an interesting trend in the market that we spend a lot of time thinking about, because I think you have some somewhat competing forces where you have growth opportunities and some of the activity that's going on to define the specialized DSPs for some of these shorter reach applications, which may be high growth opportunities and be very good opportunities to expand the TAM. But at the same time, we also have the trend in more advanced CMOS nodes getting more and more expensive for development. So we always have to balance this trend towards specialization, because volumes are increasing that allow for some level of specialization and adequate ROI, combined with the fact that development costs are going up. So you need more volumes, and so we spend a lot of time, as I'm sure a lot of our competition does as well, thinking about how do you make the right trade-offs and where's the right level of specialization.
Mm-hmm. Right. Yeah, and as I said, we're in the midst of this coherent era. I think we've got a lot of legs left, so look forward to how that develops from you and from others in the industry that are now very active here. With that, we are a little bit past the top of the hour, so I'm going to close out. Thank you, Tom. Thanks to Acacia, and thanks to everyone in the audience for tuning in today. This will conclude today's webinar.
Thanks, everyone.